In this clip, we will continue with conditional probabilities. The question from the last segment is that how to compute probability of an event A given that event B has occurred, and using the probabilities of some other events. We know how to do that by just counting the number of possible outcomes that satisfy these properties. Okay, so if you haven't thought about it for a while, please stop the video and try to figure the answer out by yourself first. It's really important that you try to think about this, because if you can figure out the answer by yourself, you understand a lot more. All right? Okay, so let's see the answer. So now, what is PA given B? We know that we have a sample space S. Okay, this is a sample space S. And we know that we have two events, A and B. This is A, and this is B, say. And we know that when we try to compute this, we know that we only consider the case when B actually occurs. So it means that all these outcomes, the outcomes outside set B, can be ignored, right? They are not relevant because we know that B occurs. Then these outcomes cannot be the outcome of these outcomes cannot be the outcome of the experiment. So it is like we can just only focus on these outcomes inside the set B. So it is like we only have the new sample space, which is B. Okay, this is A, right? So the picture would look like this. So these outcomes, can be ignored. They're not possible. Okay. Now, what's the set A in this case? So set A can be divided into two subsets. One which is this part, which cannot be occur, and the other that belongs to also in set B, right? And this is A intersection B. This part is A intersection B. So now, when the sample space is reduced to B, even A is reduced to event A intersection B. Now, what's the probabilities of A given B? Instead of counting these points, right? They're not important anymore. So we only count points in set B. Okay, these are only the possibilities, right? And among these possibilities, only the outcomes in this set A intersection B are those that we want. So we finally get this. So this is what we've just done, right? So we figure out we count the number of outcomes inside B, and the one that we want is the outcome in this set. All right. So if we do some more algebra, we know that we can just divide this by the size of the sample space, and then this part is the probability of A given A intersection B, and this is the probability that of B, right? So now we have this formula, nice formula, that talks about the probability of the conditional probability of A given B in terms of normal probabilities. Okay, in terms of A intersection B and probability of B. So this is one of the most important concepts and formula in probability theory. So let's have a few quick checks. Right. So in this case, what's the probability of picking an orange ball given that a ball with alphabet C is picked? So there are two events here, right? So one is this one, picking an orange ball. Another event, which is the given part, is this. So you want to find the probability that this event A happens given this event B has occurred. Right, so if you use this formula, then we need to figure out the probability of A and B, right, intersection B. So what's the probability that you pick an orange ball and pick a ball with alphabet C? So these are the balls, right, orange ball with alphabet C. So this is 2/7. And what's the probability of picking a ball with alphabet C? So it's these are the balls. So it's 3/7. So the answer is 2/7/3/7. So that's 2/3. So this is the same calculation, but with a more, the usage of the formula. So let's look at another check. So what's the probability of picking a black ball given the ball with alphabet B is picked? So again, there are two events. One is this. Let's call it an event A. Another is this. Let's call it this an event B. So you want to find the probability of A given B. So what's the probability that you pick a black ball with an alphabet B? So it's this. So it's 1/7. And what's the probability that you pick a ball with alphabet B? It's again 1/7. So the answer is 1/7/1/7. So that's 1. So if you know that a ball with alphabet B is picked, then you know that you pick a black ball, right? So that's what it means. Okay, so the last one. So what's the probability of picking a ball with alphabet A given that a black ball with a vowel is picked? So again, there are two events, picking a ball with alphabet A, and another is this black ball with a vowel. So let's look at the probability of A intersection B. So a ball alphabet A and pick a ball with a vowel. So a black ball with a vowel. So this is two events, right? So it looks like it's one event. It's actually an event, but it is basically an intersection of two events. So one which is pick a black ball, and another pick a ball with a vowel. So what's this probabilities? Pick a ball with alphabet A, so that's 1, and a black ball and a ball with a vowel. So it's just this one, right? This A, so it's 1/7. And what is this probability? Picking a black ball. So the black ball is this, and a black ball with a vowel is only A and E, right? So it's 2, right? So it's 2/7. So you get 1/7/2/7. So that's 1/2. All right. So that's the example. So the last quick check. So now we have a sample space, be this, and so the event A, B, and event that you pick an even number. So A is this tip 1, 2. Picking any of these numbers, and B is an every event that the number is greater than 6. Okay, so what is PA? PA is so how many numbers we have? 10, and the size of set A is 5, so it's 5/10. That's 1/2. Okay, so what's the probability of A given B? So now we have to figure out, we know probability of A, right? So we have to figure out directly A given B, or have to figure out the probability of A intersection B. So let's try to do the slow way. So A intersection B. So B is greater than 6, greater than. So these are the set. And then A intersection B is just only this 8 and 10. So it's going to be 2 over 10. And the probability of B is, what is probability that you pick something greater than 6. So you have 10 numbers, and you have 4 numbers which are good for you. So it's going to be 4 over 10. The probability that A given B is thus 2 over 10 over 4 over 10. And that's 1/2. All right. And the nice thing about this example is that this is 1/2, and this is 1/2. Okay. So what does it mean for this? Okay. So let's let me pause for a little bit so that you can think about what the meaning of this. So you have probability of A, and you have probability of A given B, and they are equal. What it means. So have you made the guess? I guess. So let's see. If you need more time, you can just stop the video, right? Okay. All right. So let's see. So it's unchanged. So if we have for some pair of events A and B, and we find out that these two probabilities are equal, so that means the probability of an event A occurring, given that B has occurred, remains the same, right? So that means even though B, whatever B occur or not, the probability that you're going to see an event A are still the same. So it means that the probability that the fact that B occurs does not change the probability that A will occur. And if we do some formula, we do some calculation, we know that then this thing imply this. Okay, by just following the definition of the conditional probability, you know that this is P of A intersection B over B, right? P of B, and then you multiply everything by P of B. So this implies this definition requires that P of B is at least is larger than 0. Otherwise, this will be like undefined. Okay, so you know this. Okay, and in this case, we will look further on this equation. But this if this happens, we say that an event A and B are independent. Okay, so what does it mean by independent? Okay, so if you look at this, it is like PA has some probability of occurring, and after you know that if B occurs, it doesn't change that, right? So it means like they are not, in some sense, they're not related. So that's why we say they are independent. So if this is true, then we say, okay, these two events are independent. If they are not independent, we say that they are dependent. So this is clear, right? So let's look at some other example. So now we have two events, A. Let A be an event that you pick an even number, and B be an event that number is greater than 4. So the question is A and B independent? So are they independent? Oh, this should be R, sorry. Okay, so the only way to figure out is to check this definition, right? If they are equal or not. Right. Okay, so it's what's the probability of A? You pick an even number, so it's 1/2. So what's the probability that you pick something greater than 4? So there are 1, 2, 3, 4, 5, 6, 6 over 10, right? So what is the probability of A intersection B? So you pick an even number and has to be larger than 4, right? So 1, 2, 3. So it's 3 over 10. And if you multiply this, you see that this is also 3 over 10, right? So they are equal. So these two events are independent. Now, if I change this to be, say, 5, what would the answer be? So now if this is 5, then this change to 5, right? And this is, again, you only have 3 numbers, which is greater than 5 and also even number. So this remain the same, but this change to 5 over 20. So that's not equal. So it means that, okay, they are not independent. And if you look carefully, so what this actually means, right? It's like, if you know in the beginning, the probability that you pick an even number is like half, right? But now you know that a number you pick is greater than 5. Okay, so it's only this. But now in this case, the number of even number it becomes 3 over 5, right? So it's getting higher than 1/2. So knowing that B occurs, somehow change your belief, right? Or change the probability that A occurs. So they have to be related somehow. So that's why we call it that they are dependent. Okay. So let me remind you again that dependent in this doesn't have to be that even B causes even A, right? There's no causal relationship here. They just, if you know that B appears, then yeah, maybe A is more likely to be appear. Okay. So look at another example. So let's A be an event and you pick a number greater than 3, and B be an event that the number is divisible by 3. So are they independent? Okay, so can you figure that out? Let me wait for a few minutes. Oh, a few seconds, sorry. All right, so what's the probability of A intersection B? Pick number greater than 3 and also divisible by 3. So 6 and 9, right? Greater than 3. So it's 2 over 10, right? Even B is divisible by 3, 1, 2, 3, so it's 3 over 10. And you pick a number greater than 3, so that's you cannot pick that, so it's 2/3, right? So it's 2 over 3, and that's again this. So it means that they are independent. If you know that you pick a number greater than 3, doesn't help you doesn't change the probability that that number is divisible by 3 or not. Okay, and again, if I change this to be let's keep this. So let's change this to be 2. Then you can do the math again. This remains the same basically. Now the probability that you pick a number greater than 2, change this to be 1, 2, 3, 4, 5, 6. So change this to be 7 over 9. And now this is not this anymore, right? So it has lower probability. So if I change this to 2, then these two events are dependent. Okay. So the last question is this: can you prove this fact with the stuff that we learned so far? So if you know that A given B equals PA, right? So that prove that this imply this fact. So this means that if you know that B occurs, doesn't change the probability that A would occur, right? So this is the counterpart of that. So you know that A occurs, and it doesn't change the probability that B occurs. All right. So see you in the next clip.